Deep inside the Coma Cluster lies a giant unlike anything we've ever seen, a sleeping black hole in NGC 489, so massive it dwarfs our entire solar system. What happens when a monster like this finally awakens? Tonight we'll explore the silent power of one of the universe's biggest black holes. If you enjoy the journey, please like, subscribe and share, and tell us in the comments, what would you ask a black hole if it could answer? Thank you for watching. Now, let's begin. Far from the Milky Way, the large-scale structure of the universe unfolds as a vast network of matter, where most galaxies do not sit alone but gather along enormous filaments that stretch across hundreds of millions of light-years. In this cosmic web, thin bridges of galaxies and dark matter link denser knots that mark the locations of galaxy clusters and superclusters, while between these crowded strands lie deep cosmic voids where relatively few galaxies are found. Gravity slowly amplifies tiny early irregularities in matter into this present-day pattern, so that over billions of years material flows along the filaments toward the densest intersections. Among these intersections, one region stands out as the realm that astronomers call the Coma supercluster, a concentration of matter that includes several galaxy clusters and groups bound into a larger-scale association. The Coma supercluster occupies a volume far beyond the local group and the nearby Virgo cluster, and lies at a distance of a few 100 million light-years from the Milky Way, so its light takes hundreds of millions of years to cross the space in between. Within this vast context, individual galaxies appear as small, bright points scattered along the filaments. Yet each galaxy contains its own enormous collection of stars, gas and dark matter gathered by gravity into a more compact system, and each carries a history that stretches back almost to the early universe. The supercluster itself does not behave as a single rigid object, because on these scales the expansion of the universe still plays an important role, and the gravitational ties between widely separated clusters are relatively weak. Instead, the Coma supercluster is understood as an overdense region within the cosmic web where several rich clusters have formed along a shared set of filaments surrounded by a lower density background of more isolated galaxies and groups that continue to drift slowly within the common gravitational field. The matter content within this region is dominated by dark matter, the unseen component that reveals its presence through gravity, while ordinary matter in the form of stars, gas and dust contributes only a smaller share of the total mass, even though it provides almost all of the light that telescopes record. Because dark matter does not emit or absorb radiation, astronomers infer its distribution by tracing the motions of galaxies and the way their paths curve under gravity, and by observing how the combined mass of clusters deflects light from still more distant background galaxies. These measurements show that the Coma supercluster sits at the intersection of several filaments of dark matter, with galaxy clusters and groups strung along these filaments like bright beads on a much larger invisible scaffold. To build this picture-wide field galaxy surveys measure positions and redshifts for hundreds of thousands of galaxies, allowing three-dimensional maps in which distance roughly follows from how much a galaxy's light is stretched by cosmic expansion. In these maps, the Coma region appears as a dense knot in redshift space, where many galaxy points cluster together and where their peculiar velocities, the additional motions on top of cosmic expansion, reveal the pull of a massive concentration of matter. Observations across different wavelengths, from visible light to X-rays and radio waves, reveal that many of the galaxies in the Coma supercluster reside in crowded environments where interactions and mergers are relatively common over cosmic time. In dense regions, encounters between galaxies can strip away gas and stars reshape stellar disks into more rounded forms and build up large elliptical systems through repeated mergers, while in the quieter outskirts galaxies can retain more of their gas and continue forming new stars for longer periods. The Coma supercluster therefore represents a mature stage in the growth of structure, where small building blocks have already combined into more massive systems, and where galaxy clusters now stand as the dominant peaks in the matter distribution on these scales, yet the overall pattern of filaments and voids continues to change slowly as time passes. Even so, the overall pattern of the cosmic web evolves only gradually, because on scales of hundreds of millions of light years, the pull of gravity and the stretching of space act over immense timescales, so that the arrangement of filaments and nodes remains broadly similar over much of the age of the universe. Measurements of galaxy redshifts and positions allow astronomers to map this three-dimensional pattern and trace the filaments that converge on the Coma region, revealing that the Coma supercluster connects onward to other concentrations of galaxies and to the broader network that extends across the observable universe. The large-scale maps of structure also link directly to measurements of the cosmic microwave background, the faint radiation left from the hot early universe, because the tiny variations seen in that background mark the seeds from which superclusters and clusters later grow under the action of gravity. By comparing the present-day distribution of structures like the Coma supercluster with these early patterns, astronomers test models of cosmic evolution and refine estimates of how much dark matter and dark energy fill space on the larger scales. Within the supercluster, rich clusters occupy the junctions where several filaments meet, and these clusters contain hundreds to thousands of galaxies bound together by their mutual gravity and the deep potential well of a shared dark matter halo. The Coma region is one of the nearest examples of such a rich cluster environment, giving astronomers an important laboratory for studying how dense surroundings affect the evolution of galaxies over long timescales, and providing a detailed view of the late stages of structure growth in the nearby universe. In this outermost view, the Coma supercluster appears as one prominent node in the cosmic web, embedded in a tapestry of filaments, clusters and voids that together define the large-scale setting in which individual clusters and their central galaxies come into being. Against this background, any single galaxy cluster is only one part of a much larger pattern that stretches far beyond the region now under consideration. Within the wider Coma supercluster, the Coma cluster itself stands out as a rich, gravitationally bound gathering of galaxies, held together by a deep pool of mass that keeps its members from drifting away, despite the overall expansion of the universe. The Coma cluster lies at a distance of about 300 million light-years from the Milky Way, so its light has been travelling toward the solar system since long before complex life appears on Earth, and what telescopes record today is a view of the cluster in an earlier cosmic time. As seen in wide-field images, the cluster presents a crowded patch of sky, dotted with many faint smudges of light, each one a separate galaxy containing billions of stars yet packed so closely in projection that some seem almost to overlap. When astronomers measure the redshifts of these galaxies and correct for the general expansion of space, they find that many share a common range of distances and move with large, peculiar velocities around a common centre, a sign that they are bound by a shared gravitational well, rather than simply lying near one another by chance along the same line of sight. The overall shape of the Coma cluster is roughly extended rather than perfectly spherical, with a denser central region and more diffuse outskirts and substructures reveal that the cluster has grown over time by the merging of smaller groups and subclusters that continue to fall inward along surrounding filaments. Within the part of the cluster where gravity has fully overcome the expansion of the universe, galaxies follow orbits that carry them through the central regions and back out again, moving at speeds of a few thousand kilometers per second, relative to the cluster center, so that close encounters and distant flybys between galaxies are common on timescales of billions of years. Many of the galaxies in the Coma Cluster are ellipticals and lenticular systems whose stars follow randomly oriented orbits in a smooth spheroidal or lens-shaped distribution rather than the ordered rotating disks seen in spiral galaxies, and these early type galaxies are especially concentrated toward the dense central regions. Spiral galaxies with well-defined arms and significant cold gas content are more often found in the outskirts and along the infiling filaments, where the local density is lower, and interactions with the central cluster environment are not yet as severe. This pattern in which dense central regions of clusters are dominated by elliptical and lenticular galaxies, while spirals prefer less crowded zones, reflects a long history in which repeated gravitational encounters, mergers and interactions with the cluster environment steadily transform galaxy shapes and star formation activity. In the Coma Cluster, some galaxies show signs of distortions, tidal streams, or truncated gas disks that point to past or ongoing interactions, while others appear relatively undisturbed but still follow the common motion dictated by the cluster potential. Observations in visible light reveal the stellar content of the cluster galaxies, while measurements at radio and other wavelengths trace the gas that remains in some systems and indicate where recent or ongoing star formation still takes place. On average, however, the Coma Cluster is considered a mature, dynamically evolved system, where the central regions host many massive galaxies that formed the bulk of their stars long ago and now shine mainly with the steady light of older stellar populations. The number of galaxies that belong securely to the cluster runs into the hundreds and likely exceeds 1,000 when faint dwarf galaxies are included, and the total mass of the cluster dominated by dark matter reaches values much larger than the combined mass of all its stars and gas. By studying the motions of galaxies within the Coma Cluster, astronomers estimate the depth of the gravitational potential and infer how much dark matter must be present to keep such a fast-moving population bound within a relatively compact region of space. These dynamical measurements show that the Coma Cluster is one of the most massive nearby clusters, providing a useful benchmark for theories of how such systems assemble over cosmic time from the merging of smaller structures. The typical time it takes a galaxy to cross from one side of the central region to the other is measured in billions of years, so each galaxy completes only a few full orbits over the age of the universe, and the present arrangement of members still carries traces of how the cluster grows. The cluster environment also includes a population of very small faint dwarf galaxies that are difficult to detect but add significantly to the total number of member systems, along with the sprinkling of ultra-diffuse galaxies that spread a modest amount of starlight over a surprisingly large area, making them extremely low in surface brightness. Some of these diffuse galaxies in Coma appear to be rich in dark matter, while others may be relatively poor in it, and their presence offers further clues to how fragile systems survive or are disrupted in a crowded cluster environment. Gravitational lensing measurements in which the combined mass of the cluster slightly distorts the shapes and apparent positions of still more distant background galaxies provide an independent way to map the mass distribution and confirm that much of the cluster's mass resides in an extended dark halo rather than in the visible galaxies alone. Throughout the cluster, galaxies move within a shared region of space that is also filled with a thin but pervasive medium and threaded by the gravitational pull of a massive dark matter, halo a context that shapes their evolution and interactions on every pass through the central regions. The Coma Cluster thus represents a dense gravitationally bound island of galaxies and dark matter within the larger Coma supercluster, a place where hundreds of galaxies orbit a common center, and where their collective gravity and motions define the overall environment long before any single galaxy within it is examined in detail. In this broader view, the part of the sky that holds the Coma Cluster is not an empty background, but a layered structure in which light from innumerable stars rides on top of the deeper influence of gas and dark matter that together sustain the cluster as a coherent system. Between the many galaxies that move within the Coma Cluster, the space is not empty, but filled with an extremely thin atmosphere of hot gas that forms what astronomers call the intracluster medium, a diffuse plasma that stretches across the cluster and follows the same deep gravitational well that binds the galaxies together. The density of this gas is far lower than the best vacuums that can be made in laboratories on Earth. Yet over the enormous volume of the cluster, it contains more ordinary matter than all of the stars in all of the member galaxies combined, so that most of the visible matter in the cluster resides not in stars, but in this hot, rarefied plasma. As the gas settles into the cluster potential, it is heated to temperatures of tens of millions of degrees high enough that atoms are stripped of most of their electrons, and the remaining ions and electrons move at very high speeds. At these temperatures, the intracluster medium emits high-energy radiation, as fast-moving electrons are deflected by the electric fields of ions, a process that produces a smooth continuum of emission, while individual elements such as iron and oxygen also add characteristic spectral lines. X-ray telescopes that observe this energetic radiation reveal the Coma Cluster as a large, roughly round patch of emission that fills the space between the galaxies with brighter regions marking denser or hotter gas near the cluster center, and fainter regions extending into the outskirts. This radiation does not come from the stars themselves, but from the hot gas that has been trapped and heated by the combined gravity of dark matter and ordinary matter in the cluster. Because the gas is so hot and so thin, it cools only very slowly, and in the absence of strong disturbances, it can remain in a nearly hydrostatic state for long periods, with pressure gradients balancing the inward pull of gravity. By measuring how the intensity and spectrum of the X-ray emission change with position, astronomers infer how the gas density and temperature vary across the cluster, and from this they estimate how much total mass is required to hold the gas in place against pressure. These studies show that the mass of ordinary matter in the intracluster medium far exceeds the mass locked into stars, yet still falls short of the total mass implied by the motions of galaxies and by gravitational lensing, so a still larger component of dark matter must dominate the cluster potential. The dark matter halo of the Coma Cluster extends well beyond the visible concentration of galaxies and hot gas, forming a roughly spherical or somewhat elongated distribution that gradually declines in density with distance from the center. This halo does not emit light, but its presence becomes clear when the speeds of galaxies are compared with the amount of visible mass that can be counted in stars and gas. The galaxies move too fast to be held together by ordinary matter alone, so an additional invisible mass component must supply the extra gravity. Gravitational lensing, in which the combined mass of the cluster slightly distorts the apparent shapes and positions of background galaxies, provides another way to probe the dark halo by tracing how space itself is curved by mass, and these measurements confirm that dark matter is the dominant contributor to the cluster's mass budget. In broad terms, the total mass of the Coma Cluster is many times larger than the mass in its stars and gas, with dark matter making up the majority hot intracluster gas, providing most of the remaining ordinary matter and stars contributing only a minor share of the total. The intracluster medium and the dark matter halo together shape the physical conditions that galaxies experience as they move through the cluster. When a galaxy with its own reservoir of cold gas falls into the cluster along a filament, it plunges into this hot, thin atmosphere and feels a wind from the intracluster medium in its own frame, a wind that can strip gas from its disk and halo through a process known as ram pressure stripping. Over time, repeated passages through the dense central regions can remove much of a galaxy's cold gas, reducing its capacity to form new stars and leaving behind a system that shines mainly with older stellar populations, a pattern that is observed in many galaxies near the core of the Coma Cluster. The stripped gas does not disappear. Instead, it mixes with the surrounding intracluster medium, enriching it with heavier elements that were forged in stars and spread by supernova explosions before being removed from their host galaxies. As a result, the hot gas in the cluster carries a record of past star formation and feedback integrated over many galaxies and many billions of years, with its chemical composition reflecting the cumulative output of countless generations of stars. The structure of the intracluster medium also bears the imprint of the cluster's growth history. Subclusters and groups that fall into coma bring their own gas halos, which are shocked and compressed when they collide with the existing cluster medium, leaving behind irregular features such as brightness enhancements, cold fronts and shock fronts visible in high-resolution X-ray images. These signatures reveal that cluster assembly is an ongoing process, not a single event, and that the hot gas responds in complex ways as new material and energy are added. In some regions, the intracluster medium shows cavities or bubbles, lower density zones that are thought to arise when energetic jets and outflows from galaxies carve channels through the gas, displacing it and lifting it outward. Radio observations often reveal synchrotron emission from relativistic particles within these bubbles, indicating that non-thermal processes also play a role in shaping the gas. Although these features are localized, they illustrate how energy released within galaxies can influence the wider cluster environment by heating or displacing gas, helping to prevent it from cooling too rapidly in the densest central regions. On larger scales, the intracluster medium appears smoother and more symmetric, approximately tracing the underlying gravitational potential set by the dark matter halo with gradual changes in density and temperature rather than abrupt boundaries. The balance between gas pressure and gravity means that the temperature of the hot gas roughly reflects the depth of the cluster potential. So the high temperatures measured in Coma confirm that it is a very massive system. At the same time, variations in temperature and density across the cluster reveal where mergers and infall have recently disturbed the gas, providing a dynamical record that complements the information drawn from galaxy distributions and velocities. Together, the hot intracluster medium and the dark matter halo define the extended cluster-scale environment that surrounds and embeds all of the individual galaxies, shaping their evolution and interactions over billions of years within the Coma Cluster. In this picture, the galaxies, though visually prominent, move as small luminous components within a far larger envelope of unseen dark matter and glowing hot gas that together set the stage for the more detailed structures found on smaller scales. Within the Coma Cluster, attention turns toward the crowded central region, where the concentration of galaxies' hot gas and dark matter reaches its highest levels, and where the combined gravity carves out the deepest part of the cluster potential well. In this inner zone, the sky as seen from a hypothetical vantage point inside the cluster would be populated by many large galaxies appearing relatively close together, their diffuse halos overlapping in projection, so that the separation between systems seems smaller than in more sparsely populated cosmic fields. The central region is not sharply bounded, but its character changes gradually as one moves inward from the outskirts, with the number density of galaxies increasing and the intra-cluster medium growing denser and hotter toward the center. In the Coma Cluster, this heart of the system is marked by the presence of several very massive galaxies, including 2 dominant ellipticals that stand out by their brightness and size. Among them, NGC 4889 occupies a prominent place as one of the brightest cluster galaxies sharing the central domain, with another giant elliptical often designated as a co-equal dominant member. These central galaxies do not sit alone. They are embedded in a rich swarm of smaller companions, including intermediate mass ellipticals, lenticulars, and numerous dwarf galaxies that orbit within the same deep gravitational well. Their orbits and spatial distribution trace the overall shape of the cluster core, which appears somewhat elongated rather than perfectly spherical, hinting at the history of past mergers and continuing infall along preferred directions tied to the surrounding filaments. The hot intra-cluster medium in this region forms a bright, centrally concentrated component when seen in high-energy radiation, with emission peaking roughly where the galaxy density is highest. The gas is compressed and heated as subclusters and groups fall in, and as a result its temperature and pressure reach some of their largest values near the center, reflecting the depth of the potential well. By mapping the intensity of this emission, astronomers find that the contours of gas density wrap around the central galaxies and extend outward, indicating that these galaxies lie very near the bottom of the gravitational basin that holds the cluster together. Superposed on the light of individual galaxies, there is also a faint diffuse glow known as intra-cluster light, produced by stars that no longer belong to any single galaxy, but instead drift freely within the cluster core. These stars are believed to have been stripped from their original hosts during close encounters and mergers over billions of years, and they now contribute a smooth background that is most intense near the central region, where interactions have been most frequent. Deep images show that the halos of the central ellipticals blend almost seamlessly into this diffuse component, making it difficult to draw a sharp line between where a galaxy ends and the intra-cluster stellar population begins. NGC 489, like its central companion, exhibits an extended, nearly featureless stellar envelope that fades gradually with radius and helps to define the luminous core of the cluster. In visible light, these giant ellipticals dominate the appearance of the central field, their diffuse bodies spanning distances many times larger than the optical size of a typical spiral, such as the Milky Way, and their combined light setting the overall brightness scale of the region. The density of galaxies near them is high, so in deep exposures many smaller systems can be seen scattered around the dominant pair, some showing signs of tidal distortion or asymmetric light profiles that hint at recent interactions. The distribution of dwarf galaxies also peaks toward the center, where the cluster tidal field is strongest, although the faintest of these systems remain difficult to detect even in long integrations. As groups and individual galaxies fall into coma along surrounding filaments, they tend to deposit their most massive members and stripped stars into the central region, gradually building up the halos of the brightest cluster galaxies and the intra-cluster light. This process continues over long timescales, so the central region of Coma is both a repository of material accumulated from many past infall events and a site where new material is still being added. Kinematic studies show that the velocities of galaxies in the core are large, with random motions in different directions that reach thousands of kilometers per second. Yet the overall distribution remains statistically stable over long periods, indicating that the core is close to a dynamical equilibrium. In such a state, the central galaxies, including NGC 4889, move only slowly with respect to the cluster center of mass, while smaller galaxies follow more extended, often eccentric orbits that carry them through the core and back out into the outskirts. Some of these paths bring galaxies close enough to the dominant ellipticals that tidal forces reshape their outer regions, or even fully disrupt the smallest systems, feeding additional stars into the halos of the giants and into the intracluster component. The dark matter halo that envelopes the core does not appear directly in these images, yet its gravity is what holds the entire arrangement together, setting the speeds at which galaxies move and shaping the overall profile of the gas and stellar light. In effect, the luminous components in the central region act as tracers that reveal the underlying mass distribution, their spatial and velocity patterns, offering clues to how the core assembles and relaxes over cosmic time. The interplay between the dense population of galaxies, the hot gas, and the dark matter halo produces a central region where physical conditions differ markedly from those in the lower density outskirts or in the general field outside clusters. Here, the probability of strong gravitational encounters is much higher. The intracluster medium is brighter and hotter, and the combined light of overlapping stellar halos creates a soft diffuse glow that fills much of the central volume. Within this luminous environment, NGC 4889 stands as one of the key tracers of the cluster core, marking both the location of the deepest part of the potential well and the outcome of many merging events that have built up its present mass and extended envelope. To understand the detailed structure and history of this galaxy, attention now shifts from the broader cluster core to NGC 49 itself, treating it as a single enormous stellar system embedded within the bustling heart of the Coma Cluster. Seen as a single object within the crowded heart of the Coma Cluster, NGC 4889 appears as a giant elliptical galaxy whose smooth glow dominates a large patch of sky, an extended ellipse of light that gradually fades into the surrounding intracluster background. Unlike a spiral galaxy, which displays a bright disk, winding arms, and distinct structural components, this system presents no obvious internal pattern. When viewed in broad overview, only a continuous distribution of stars whose brightness is highest near the center and steadily decreases outward. Deep images reveal that the galaxy stretches across a region that, if placed at the distance of the Milky Way's neighbors, would span a large angle in the sky far greater than the apparent size of most single galaxies seen in isolation. The stellar envelope of NGC 4889 is elongated rather than perfectly round, with its isophotes or lines of equal brightness forming slightly flattened ellipses that trace how stars are distributed in 3 dimensions. This overall shape places it in the family of massive elliptical galaxies that sit near the centers of rich clusters and often grow through the merging of many smaller progenitors over long spans of cosmic time. The surface brightness profile, which describes how the luminosity falls off with radius, shows a steep central concentration that then transitions to a more gradual decline at larger distances from the center, so that the outer regions still contribute a significant fraction of the total light, even though the glow there is very faint. When astronomers measure the total luminosity of NGC 4889 in visible bands and compare it with that of the Milky Way, they find that this cluster giant radiates with a brightness that exceeds the Milky Way's by a large factor, indicating a much larger overall stellar mass. While the Milky Way combines a disk, a central bulge, and a dark matter halo into a system that holds perhaps a few 100 billion stars, NGC 4889 contains several times that number gathered into a more nearly spheroidal configuration, whose stars follow orbits that lack the orderly rotation seen in a disk. In broad terms, this means that the galaxy is not supported primarily by rotation, but by the random motions of its stars in many directions, a state that astronomers call pressure support, in contrast with the rotational support of a spiral disk. Photometric observations across different colors show that NGC 4889 has a relatively red global color, compared with many disk galaxies, a sign that its light is dominated by older cooler stars rather than by hot young blue stars associated with recent star formation. This red smooth appearance reflects a history in which most of the galaxy's star formation takes place early, followed by a long period during which new star birth is strongly reduced or almost shut down, leaving behind a population of aging stars that gradually evolve and fade. The lack of obvious dust lanes or clumpy star-forming regions in large-scale images reinforces this picture of a galaxy in which cold gas, the raw material for new stars, is limited in the main body, and does not shape the visible structure to the same extent as in gas-rich disks. At the same time, subtle changes in color and surface brightness with radius suggest that the outer halo of NGC 4889 may contain stars with somewhat different histories and chemical compositions than those nearer the center, perhaps reflecting the accretion of smaller galaxies whose stars are deposited preferentially in the outskirts during minor mergers. Measurements of its apparent size on the sky, combined with its distance, show that the galaxy's stellar envelope reaches out over many tens of kiloparsecs, a scale that comfortably exceeds the optical radius of the Milky Way, and places NGC 4889 among the largest known galaxies in the nearby universe. Within this extended envelope, the central regions rise steeply in brightness, creating a high surface brightness core that dominates shorter exposure images and often saturates the central pixels in deep observations, while the faint outskirts only appear clearly when long integrations and careful processing are used to reveal them against the background. The transition from the bright inner body to the diffuse outer halo is gradual rather than sudden, underscoring the difficulty of defining a sharp physical boundary for such a system. Instead, astronomers adopt practical definitions based on how far the measurable light extends above the sky level. Comparisons between NGC 4889 and other brightest cluster galaxies show that it fits the pattern of central ellipticals that are extremely luminous and massive, and that often occupy nearly stationary positions near the dynamical centers of their clusters. Its location close to the peak of the intracluster medium emission, and the clustering of nearby galaxies around it, both support the view that it lies very near the bottom of the Coma Cluster's gravitational potential. Structural analyses that fit standard models to its surface, brightness profiles such as concentrated profiles often used to describe elliptical galaxies, indicate high central concentrations and extended outer wings, consistent with a history of growth through successive mergers that deposit stars over a wide range of radii. In this sense, NGC 4889 can be regarded as a visible record of the Coma Cluster's assembly, its enormous stellar mass and size reflecting the cumulative contributions of many progenitor systems that have been drawn into the cluster core and absorbed over billions of years. When its total stellar mass is estimated by combining luminosity measurements with reasonable assumptions about the mass carried by a typical population of stars of various types and ages, the result places NGC 4889 among the most massive galaxies in the local universe, with a stellar content that greatly outweighs that of more familiar systems such as the Milky Way or Andromeda. The galaxy's smooth outer isophotes and overall symmetry indicate that on large scales it has reached a state close to dynamical relaxation, where the distribution of stars no longer shows strong asymmetries or obvious scars from recent major mergers. Even those smaller scale features and detailed kinematic studies reveal more subtle complexities. In images that go deep enough to trace both the main body and the surrounding intracluster light, the luminous halo of NGC 4889 appears to blend into the diffuse glow that pervades the cluster core, making it difficult to assign a clear separation between the galaxy and the shared stellar background. This blending underscores how intimately the galaxy is linked to its environment, yet as a distinct concentration of light and mass, it remains recognizable as a single, dominant elliptical system whose overall structure and brightness set it apart from its neighbors. From this perspective, NGC 4889 stands not only as a bright member of the Coma Cluster, but as a giant elliptical galaxy whose size, luminosity, and smooth global morphology encapsulate the outcome of many cycles of galaxy growth in a dense cluster environment, providing a natural next step toward examining in more detail the stars that populate its interior and the conditions they reflect. Within the smooth envelope of NGC 4889, the apparent simplicity of its light hides the fact that this galaxy is an enormous collection of individual stars, stellar remnants, and star clusters, whose combined output produces the diffuse glow seen in images. When the integrated light of the galaxy is spread into a spectrum and examined in detail, absorption features from many types of atoms and ions appear superposed on a continuum that is relatively red compared with that of galaxies where new stars are still forming at a high rate. This combination of overall color and spectral features points to a stellar population that is dominated by old, long-lived stars with only a very small contribution from hot, massive, short-lived stars that would shine strongly in blue and ultraviolet light. In broad terms, most of the light of NGC 4889 today comes from stars with masses comparable to or smaller than the mass of the Sun stars that spend many billions of years fusing hydrogen in their cores and evolve only slowly. More massive stars which burn through their fuel quickly and end their lives in powerful explosions would have completed their evolution long ago if they formed early in the history of the galaxy, leaving behind compact remnants such as white dwarfs, neutron stars, and stellar mass black holes that add to the mass budget but contribute relatively little to the present-day light. The dominance of old stars is also reflected in the lack of obvious blue star-forming regions, luminous young clusters or bright nebulae within the main body of the galaxy when it is imaged with sufficient resolution. Instead, the light distribution appears smooth and steady, with only subtle changes in color and brightness that reflect gradual variations in the mix of stellar ages and chemical compositions from the center outward. Population synthesis models which combine the expected light from stars of different masses and ages, according to simple assumptions about the history of star formation, are used to match the observed colors and spectra of NGC 4889, and these comparisons support a picture in which much of the stellar mass forms relatively early in intense episodes of star formation, when the universe is younger and gas supplies are more abundant. After these early phases, the rate at which new stars are born declines sharply, either because the cold gas is consumed heated or expelled, and the galaxy transitions into a state where its light is dominated by the aging stellar population already in place. As a result, by the present epoch, the main body of NGC 4889 contains relatively few very young stars, and the ongoing star formation rate is thought to be low compared with that seen in gas-rich spiral galaxies. The stars that make up this dominant population span a range of chemical compositions, often described in terms of metallicity, a quantity that measures the fraction of matter made of elements heavier than hydrogen and helium. In NGC 4889, as in many massive ellipticals, the average metallicity of stars is relatively high, especially near the center, indicating that the gas from which they formed has been enriched by successive generations of stellar evolution and supernova explosions. Spectroscopic measurements show strong absorption lines from elements such as magnesium and iron, and the relative strengths of these lines suggest that much of the star formation in the galaxy proceeds rapidly on timescales short enough that contributions from different types of supernova imprint characteristic abundance patterns. Toward larger radii, the mean metallicity tends to decrease, somewhat consistent with the idea that the outer parts of the galaxy include a higher fraction of stars that originated in smaller, less enriched systems that were later accreted and dispersed into the halo. Within the bright main body, however, the dominant impression is of an old metal-rich stellar population whose light has a fairly uniform red colour when averaged over large regions, even though small-scale variations remain. The total number of stars required to produce the observed luminosity is enormous. When the integrated light is converted into a stellar mass estimate using plausible mass-to-light ratios for old populations, the main body of NGC 4818 is found to contain several times the stellar mass of the Milky Way, implying that hundreds of billions or possibly more than a trillion individual stars contribute to its glow. In such a population, the most numerous stars by far are low-mass cool dwarfs that contribute modest amounts of light individually, but make up a large fraction of the total mass, while a smaller number of more luminous intermediate mass stars supply a disproportionate share of the visible and near-infrared radiation. Evolved stars such as red giants and horizontal branch stars also play an important role in shaping the spectrum, because even though they are less numerous than main sequence stars, their large radii and high luminosities make them bright contributors to the integrated light. These evolved phases reflect the internal evolution of stars that have already exhausted hydrogen in their cores and moved on to later stages of nuclear burning stages that are especially sensitive to the star's initial mass and chemical composition. The mixture of such stars in NGC 4889 therefore carries information about the ages and enrichment history of its stellar population as a whole. Clusters of stars also contribute to the stellar content. Within and around the main body, there exists a rich system of globular clusters, compact, roughly spherical groupings of hundreds of thousands of stars bound tightly by their own gravity. Although each globular cluster is tiny compared with the full galaxy together, they add a distinct component to the light and mass budget of NGC 4889, and their spatial distribution and colours provide further clues to the galaxy's formation. Many of these clusters have old ages comparable to those of the oldest stars in the galaxy, and their metallicities often divide into subpopulations, with some clusters appearing more metal-poor and others more metal-rich. This pattern suggests that globular clusters form in different episodes, perhaps linked to major stages of galaxy assembly, and that some are brought in by accreted satellites, while others form in situ within the main body. In the bright central regions, it becomes more difficult to distinguish individual clusters against the very high background of starlight, but at intermediate radii they can be resolved and counted, revealing a population that extends well beyond the visible core and out into the surrounding halo. Beyond clusters, the galaxy contains the usual spectrum of stellar remnants expected in an old population. White dwarfs. The compact embers of low and intermediate mass stars are numerous but faint, and together they represent a substantial reservoir of mass that emits mainly in optical and ultraviolet bands at relatively low luminosities. Neutron stars and stellar mass black holes formed in the deaths of massive stars are far harder to detect directly, but in some cases they may reveal themselves through X-ray emission when they accrete matter from a binary companion star. Even when they remain unseen, their gravitational influence is folded into the overall mass profile that is inferred from the motions of visible stars. The combined effect of all these components is a stellar population that is both complex in detail and simple in its broad characteristics. Most of the mass resides in old low-mass stars, and their remnants, most of the light comes from somewhat more luminous, evolved and intermediate mass stars, and only a narrow slice of the full stellar life cycle is still played out in real time through ongoing star formation. On the scale of the entire galaxy, this mature stellar content gives NGC 4889 its smooth reddish appearance, and underpins the structural scaling relations that link its luminosity size and internal velocities. These relations observed in many massive ellipticals show that brighter galaxies tend to have larger effective radii and higher characteristic stellar speeds, and NGC 4889 occupies the bright massive end of this sequence. The detailed kinematics that reveal those speeds are examined more closely in later views of the inner regions, but already from the standpoint of its stellar content alone, NGC 4889 can be understood as an enormous old and relatively quiescent stellar system whose present light is the integrated result of many past episodes of star birth and chemical enrichment within the dense environment of the Coma Cluster. Within and around NGC 4889, the bright main body of the galaxy is wrapped in an extended halo, whose faint light fades only slowly into the surrounding glow of the Coma Cluster core, creating a broad transition zone where it becomes difficult to say exactly where the galaxy ends and the intracluster environment begins. In deep images taken with long exposures and careful processing, the outer regions of NGC 4889 appear as very low surface brightness esophotes that stretch far beyond the radius. Where the galaxy is obvious in shorter observations, their contours slightly elliptical and aligned with the inner structure, but becoming more irregular in the far outskirts. Within this halo, stars are spread over such a large volume that the local density of light is extremely low, yet when all of these outer zones are integrated together, they contribute a meaningful fraction of the total luminosity of the galaxy and carry important clues to its formation history. The colors of the halo light measured by comparing its brightness in different filters tend to be somewhat bluer or more metal poor than the central regions, suggesting that many of the stars there originate in smaller, less enriched systems that are later accreted and stripped of their own compact structure, leaving their stars to orbit as part of the extended envelope. These minor mergers and tidal interactions deposit stars at large radii, building up a halo that is structurally distinct from the inner body, yet still bound to the same overall gravitational potential. The orbits of halo stars are likely to be highly varied, ranging from elongated paths that carry them far from the center to more confined trajectories, and together they create a kinematic pattern that differs from the more isotropic or mildly anisotropic motions found deeper in the galaxy. Observationally, such motions are inferred indirectly, for example, through the velocities of globular clusters and planetary nebulae that act as tracers because individual halo stars in NGC 4889 are too faint and distant to measure separately. Surrounding and interleaved with this stellar halo is a rich system of globular clusters that extends well beyond the bright core and reaches out into the outer parts of the galaxy and into the cluster environment. These globular clusters appear in images as tiny, nearly point-like sources whose colors and magnitudes can be measured to determine their general properties and to distinguish them from foreground stars and background galaxies. In NGC 4889, as in many massive cluster centrals, the number of globular clusters is very large, with the total population estimated to reach into the many tens of thousands, making the galaxy one of the richest known in terms of such clusters. Their spatial distribution follows the galaxy light in broad outline but is more extended so that the density of clusters at large radii remains significant, even where the surface brightness of the diffuse stellar halo has dropped to low levels. When their colours are plotted, the globular clusters often separate into at least two broad groups, one more metal-poor and typically bluer, and another more metal-rich and redder, a pattern that points to multiple phases of cluster formation, linked to different episodes in the assembly of the galaxy. Metal-poor clusters are thought to form early, perhaps in low-mass progenitor systems, or in the initial collapse of the main halo, while metal-rich clusters form later in more enriched gas, possibly during major star-forming events or mergers that build up the central body. In the case of NGC 4818, the large number of both types suggests a complicated assembly history in which many building blocks contribute their own cluster systems, some of which survive as discrete objects, while others are destroyed, donating their stars to the diffuse halo. At still larger radii, the globular cluster system gradually merges into the intracluster population of clusters that orbit in the wider potential of the Coma Cluster, rather than being bound solely to NGC 4889, making it challenging to draw a clean dividing line between galaxy-associated and cluster-wide components. Alongside the globular clusters, a variety of small companion galaxies or satellite systems can be found in the vicinity of NGC 4889, ranging from intermediate mass ellipticals and lenticulars to faint dwarfs that barely rise above the background light. Some of these satellites show tidal features such as distorted isophotes, extended streams or asymmetries that indicate that they are currently being stripped or have recently undergone strong gravitational encounters with the central galaxy or with the overall cluster potential. When a small galaxy passes close to NGC 4889, the tidal field can stretch and distort it, pulling stars out along leading and trailing directions that line up roughly with its orbit, while its gas may be removed both by tidal forces and by interaction with the intracluster medium. Over many such encounters, the most fragile satellites can be fully disrupted, contributing their stars to the extended halo and to the intracluster light, while more robust systems survive but lose mass and change structure. Deep imaging of the Coma Cluster core reveals faint streams and shells that likely trace the remnants of past accretion events around central galaxies, and NGC 4889 is expected to host similar features, although the exact pattern depends on the detailed history of infall and the orbits of the accreted systems. Ultra-diffuse galaxies and ultra-compact dwarfs, which are extreme in opposite ways, also populate the region around NGC 4889 and the cluster core more generally. Ultra-diffuse galaxies spread a modest stellar content over a very large area, resulting in extremely low surface brightness objects that are difficult to detect, but may have been strongly altered by tidal forces, while ultra-compact dwarfs are small, dense systems that may represent the stripped nuclei of larger galaxies. Both types of objects provide additional pathways by which stars can be transferred from satellites into the halos of central galaxies and into the intracluster medium. The intracluster light itself, which permeates the cluster core, is closely linked to the halo of NGC 4889 in both space and origin. In regions very near the galaxy, the diffuse background is dominated by stars that are still gravitationally bound to NGC 4889, forming its extended envelope. Farther out, the contribution from stars that orbit the cluster center, rather than any single galaxy, becomes more important, yet the transition between these regimes is smooth, and in practice it is often defined by convention or by the limits of observational sensitivity. This shared faint light is produced by stars that have been liberated from their parent galaxies by tidal interactions, mergers, and the overall cluster tidal field, and they move on orbits that crisscross the cluster core on large scales. In a long exposure image, their combined glow forms a soft background against which the bright central galaxies stand out, but there is no sharp visual boundary separating one component from the other. For NGC 489, this means that its halo gradually blends into the intracluster light, reinforcing the idea that the galaxy and its environment are deeply interconnected through the processes of stripping, merging, and accretion that operate over billions of years. The outer halo globular cluster system, satellite population, and intracluster light together record the history of matter flows into and out of the central galaxy, preserving in their spatial and chemical properties a fossil record of how NGC 4889 has grown within the dense core of the Coma Cluster. Even without resolving individual halo stars, astronomers can read this record statistically by measuring light profiles, colors, and the distributions of clusters and satellites, building up a coherent picture in which the extended structures around NGC 489 emerge as key components of the galaxy, rather than as a separate peripheral addition. In this way, the halo and its associated populations complete the view of NGC 489 as not just a bright central body but as a galaxy with an extensive complex outer structure that merges imperceptibly into the shared stellar background of the cluster core. Within the vast stellar body and extended halo of NGC 489, the content and behavior of gas and dust differ markedly from those in gas-rich spiral galaxies, and these differences help to explain why the galaxy's present state is so quiet, compared with the more actively star-forming systems found in less extreme environments. In the main body of NGC 4889, cold gas in the form of neutral atomic hydrogen and molecular clouds is scarce, at least compared with the large reservoirs seen in spirals where stars are still forming at significant rates. Radio observations that are sensitive to these cold components find only weak or undetectable signals from the galaxy, indicating that any remaining cold gas mass is small relative to the stellar mass. Without a substantial supply of dense, cool clouds, the classic cycle in which gas collapses under gravity to form new stars and then is replenished by infalling material cannot proceed at the same level as in galaxies with rich gas disks. Instead, the present-day interstellar medium of NGC 4889 is dominated by much warmer and more tenuous phases embedded in and interacting with the hot intracluster medium that fills the core of the Coma Cluster. Evolved stars throughout the galaxy continually lose some of their mass through slow stellar winds, returning gas enriched with heavier elements to the surrounding space. In a galaxy like NGC 4889, where the stellar population is old and numerous, this mass loss supplies a steady but diffuse source of gas. However, the environment into which this gas is injected is not a cool disk, but a region permeated by high thermal energy, both from the galaxy's own gravitational potential and from the surrounding hot cluster atmosphere. As the stellar ejecta leave their parent stars, they encounter this hot medium and are quickly heated, mixed, and in some cases driven outward rather than settling into dense clouds. Supernova explosions from the last remaining massive stars and from older stellar populations such as Typea supernovae, originating in binary systems, also inject energy into the gas, further raising its temperature and stirring it on various scales. Over time, these processes help to maintain a warm or hot interstellar component that is less prone to gravitational collapse into new star-forming regions. X-ray observations of the central parts of the Coma Cluster show that NGC 4889 is embedded in a bright hot atmosphere, and in some analyses a somewhat cooler, denser corona of gas may be associated with the galaxy itself, nested within the hotter cluster medium. This galactic-scale corona, if present, represents gas that remains bound more tightly to the galaxy's own potential. Well, yet its temperature is still high enough that it emits predominantly in X-rays rather than in optical line emission, characteristic of cooler gas. The balance between this bound gas, the broader intracluster medium, and the energy input from stars and previous energetic events determines whether gas can cool and condense or whether it remains in a hot diffuse state. In NGC 4889, the evidence points toward a regime where radiative cooling is largely offset by heating and by mixing with hotter surroundings, so that large-scale flows of cooling gas condensing into the central regions are not dominant features of the present-day environment. As a result, the main body of the galaxy does not show strong signatures of widespread cool gas clouds or of luminous nebulae ionized by young massive stars. Optical spectra of the galaxy's integrated light reveal only weak or absent emission lines from warm gas, and the broad colours remain consistent with an old stellar population rather than with a significant admixture of very young stars. This suggests that any ongoing star formation is confined to very low levels, perhaps to small localized regions or to residual gas pockets that do not alter the global appearance of the galaxy. In contrast, galaxies that reside in less hostile environments or that retain large cold gas disks show prominent H-alpha emission and ultraviolet light from young stars, features that are largely subdued or missing in NGC 4889. Dust, which often traces cold gas and star-forming regions, is also limited in the main body of NGC 4889. High-resolution imaging can in some giant ellipticals reveal patches lanes, or small disks of dust near the center remnants of past accretion events, or internal processes that have not yet fully mixed or been destroyed. In the case of NGC 4889, any dust structures that exist appear relatively modest and do not dominate the global morphology. Without large opaque dust lanes cutting across the stellar body, the galaxy's light distribution maintains its smooth, regular appearance in visible wavelengths. The total dust mass inferred from infrared observations is small compared with that in a spiral galaxy of similar stellar mass, and the dust that is present is likely to be constantly processed by sputtering in the hot gas, by shocks and by radiation, gradually eroding grains and returning their material to the gas phase. The scarcity of both cold gas and dust is closely linked to the dense cluster environment. As NGC 4889 forms and grows near the center of the Coma potential, well-infalling gas-rich galaxies can be stripped of their outer gas layers by ram pressure as they plough through the intracluster medium, a process that removes fuel not only from satellite systems, but also limits the amount of fresh cold gas that can be delivered intact to the central regions. Tidal interactions and mergers that build up NGC 4889's stellar mass also tend to heat and redistribute gas, sometimes funneling it inward, but also making it more vulnerable to stripping and heating by the ambient medium. Over cosmic time, these mechanisms collectively reduce the cold gas reservoir associated with the central galaxy, driving it toward a state where ongoing star formation is suppressed. At the same time, the hot intracluster medium exerts a confining pressure that can help retain some of the hotter gas around the galaxy, especially in the form of a central corona, but this retained gas remains too warm and too ionized to collapse easily into new stars. The present-day radio and X-ray signatures of NGC 4889 where detected reflect these conditions. Extended radio structures associated with energetic outflows or strong ongoing nuclear activity are not the dominant feature of the galaxy's appearance at cluster scales, and the X-ray emission linked specifically to the galaxy is relatively modest compared with the broader cluster emission, suggesting that any current energy input from compact central sources or from recent starburst activity is limited. Instead, the observable properties point toward a slowly evolving system in which the main energetic exchanges involve the gentle recycling of stellar mass loss into a hot atmosphere and its interaction with the surrounding intracluster gas, rather than dramatic episodes of rapid accretion or intense star formation. On human timescales, the appearance of NGC 4889 is effectively static. The distribution of stars' gas and dust changes only gradually with secular processes like stellar evolution, weak gas flows, and the long-term mixing of the interstellar medium acting over tens of millions to billions of years. No bright large-scale star forming rings or spiral arms emerge to alter the morphology, and no strong dust obscuration events transform the visible structure. Instead, the galaxy maintains the character of a massive old elliptical embedded in a dense cluster core, its luminous body tracing the accumulated history of past growth, while its present interstellar content reflects a state of relative quiescence. In this environment, the main day-to-day influences on the galaxy arise from the steady interaction between its aging stars and the surrounding hot atmosphere, and from the slow infill and disruption of small companions, rather than from ongoing major rearrangements driven by cold gas. The quiet interstellar medium of NGC 4889 thus forms a key part of its present identity, a mature gas-poor, dust-poor giant elliptical whose main body is dominated by old stars and by a hot diffuse gaseous component that shows little sign of large-scale current star formation. This sets the stage for a closer look at the inner stellar structure, where changes in the light profile and in the motions of stars reveal how the galaxy's central regions differ from its outer body, even within this overall calm and evolved context. Deep within NGC 4889, the broad, smoothly declining light of the outer body gives way to a more complex inner structure, where the distribution of stars changes character over the innermost few thousand light years and offers important clues to the galaxy's history. When astronomers measure the surface brightness profile of the galaxy with high-resolution imaging and plot how the intensity of starlight varies as a function of radius all the way into the central arc seconds, they find that the inner profile does not simply continue the steep rise expected from an extrapolation of the outer law. Instead, the increase in brightness slows in the innermost region, producing what is called a depleted or chord profile, in which the central light density is lower than would be predicted if the outer trend continued unbroken. This shallow inner cusp appears as a gentle flattening in the surface brightness curve, and it defines a core radius or break radius inside, which the light density rises more slowly toward the center than outside. In images, this structure does not appear as an obvious hole or gap because the surface brightness near the center remains very high compared with the rest of the galaxy, but careful analysis shows that there are fewer stars in the inner region than a simple extrapolation of the outer profile would suggest. The existence of such a core indicates that processes have acted specifically in the central zone to rearrange or remove stars from low-energy orbits, carving out a region of reduced stellar density while leaving the broader envelope intact. High-quality observations taken with space-based and large ground-based telescopes resolve the inner light distribution of NGC 4889 well enough to reveal this shallow core structure. The isophotes remain nearly elliptical, with only subtle deviations from perfect symmetry, but their spacing reflects the slower rise in brightness inside the break radius. This pattern is common among the most luminous elliptical galaxies at the centers of rich clusters, where central cores are larger and more pronounced than in lower mass systems. In NGC 4889, the physical size of the core is measured in thousands of light-years, making it a substantial region that contains a large number of stars even after depletion. The fact that the surface brightness profile bends downward relative to the outer law at this radius suggests that the inner stellar distribution has been modified in a systematic way, not just by random fluctuations. Dynamical models and theoretical studies indicate that repeated mergers between massive galaxies can naturally produce such cores. When two large galaxies, each with its own central concentration of stars and a central massive compact object, merge within a cluster environment, their central regions eventually sink together toward the new common center under the influence of dynamical friction. As the compact objects spiral inward and form a bound pair, they begin to interact with the surrounding stars gravitationally. Stars that pass close to the binary can be accelerated and flung out to larger radii, or even ejected from the system, carrying away energy and angular momentum, and allowing the pair to shrink further. This three-body scattering process tends to preferentially remove stars on low angular momentum orbits that plunge deep into the center, gradually depleting the stellar density in the inner region, and creating a core of reduced light compared with the outer profile. Successive mergers can repeat this process, enlarging the core and increasing the amount of missing light, so that the most massive ellipticals in dense environments end up with the largest and most depleted centers. In the case of NGC 4889, the size and depth of the observed core suggest that it has experienced multiple such episodes during its growth, consistent with its status as a central galaxy in a rich cluster where mergers are common over long timescales. The stellar motions in the inner regions provide further insight into how the core has formed and how it is maintained. Spectroscopic measurements across the face of the galaxy reveal the line of sight velocities and velocity dispersions of stars at different radii, allowing astronomers to map how fast stars move and how their orbits are arranged in 3 dimensions. In the outer parts of NGC 4889, the velocity dispersion is already high, reflecting the large mass of the galaxy and the strong gravitational field that holds its stars. As one approaches the center, this dispersion often rises even further, indicating that stars near the core move at very high speeds in the deep central potential. However, the detailed pattern can be more complex than a simple, monotonic increase. In some directions there may be signs of anisotropy, where stars prefer particular orbital families such as more radial or more tangential paths, and in some massive core galaxies hints of kinematically distinct components or subtle rotation may be present. For NGC 4889 models that fit both the light profile and the kinematic data suggest that the central region has a mix of orbital types, but with fewer stars on very radial orbits that plunge straight through the center, consistent with a history in which such stars are scattered away by central dynamical processes. This orbital structure helps maintain the depleted core because orbits that avoid the very center do not refill it with stars as efficiently as a more isotropic distribution would. The luminous matter in the inner few thousand light-years is not limited to the smoothly varying stellar component. Within this region there may also be a modest population of compact star clusters, nuclear remnants of past accreted systems and faint dust features, although in NGC 4889 such additional structures remain subtle compared with the dominant smooth background. Any small-scale dust patches that exist can produce minor irregularities in the surface, brightness or color maps, but they do not strongly alter the overall chord profile. The gas content, as noted earlier, is low, so the central light is not significantly contaminated by emission from bright ionized gas clouds or active star-forming complexes. This relative simplicity makes NGC 4889 an important case for dynamical modeling, because the inner light can be interpreted primarily in terms of stars moving in a combined potential set, by the stellar mass, the dark matter, and the central compact mass. Advanced modeling techniques such as orbit superposition methods use the observed light and velocity fields to construct detailed three-dimensional dynamical models in which the distribution of stellar orbits is adjusted until the model matches the data. In such models, the presence of a central core and high central velocity dispersion can be explained only if a very massive central object is included, and the size of the core together with the kinematic constraints helps determine the characteristics of the central potential. Even without focusing yet on that central compact mass itself, the observed structure of the inner light profile and the kinematics show that the gravitational field in the inner regions is extremely deep and that it has played an active role in shaping the stellar distribution. The inner light profile also connects to broader empirical relationships observed in elliptical galaxies. When the amount of missing light in a core is compared with the total luminosity and with global properties such as stellar mass and velocity dispersion patterns emerge that indicate a link between the scale of the core and the amount of mass that has been concentrated at the center. NGC 489, with its large core and high luminosity, lies at the extreme end of these trends, reinforcing the idea that central depletion grows with galaxy mass and with the cumulative impact of merger-driven dynamical evolution. In this sense, the core of NGC 4889 acts as a fossil record of past interactions in the densest part of the Coma Cluster, encoding in its shallow inner profile the combined effects of many merging events and of the deep potential that governs stellar motions near the center. Within the inner few thousand light years, then NGC 4889 departs from the simple extrapolation of its outer structure and reveals a distinct central zone, a high surface brightness yet depleted core, where stellar density and orbits bear the imprint of strong gravitational processes that have acted repeatedly over cosmic time. This inner structural change marks the transition from the broad body of the galaxy to the nuclear regions in which the gravitational influence of the central mass becomes especially important, a region where the motions of stars are strongly guided by the deepest part of the potential well carved out within the heart of NGC 4889, in the inner regions of NGC 4889, where the surface brightness profile bends into a shallow core and the gravitational field is strongest. The motions of stars carry most of the information that astronomers have about the mass distribution that cannot be seen directly. Each star follows an orbit set by the combined pull of the galaxy's stellar body, its dark matter halo, and the compact mass at the very center, but at the great distance of the Coma Cluster, individual stars cannot be tracked one by one. Instead, the light from many stars is blended together within each small patch of sky, and their motions are inferred statistically from how their combined spectrum is broadened and shifted. In practice, observers place spectrographs on large telescopes and record the integrated light from narrow slits or from arrays of tiny spatial elements that together cover the inner parts of the galaxy, building up a two-dimensional map of how the spectrum changes from place to place. The absorption lines imprinted by stellar atmospheres, which appear as dark features on top of the continuous glow, are slightly displaced in wavelength by the Doppler effect, when stars move toward or away from the observer, and when many stars with different velocities contribute to the same resolution element. These lines are broadened into smooth, rounded profiles. By measuring the shift of the line centers, astronomers recover the mean velocity of the stars along the line of sight at each position, revealing any large-scale rotation or streaming motions, while the width of the lines reveals the velocity dispersion, a measure of how widely the individual stellar speeds are spread around that mean. In a galaxy like NGC 4889, where random motions dominate over ordered rotation, the velocity dispersion is high even in the outer parts, indicating that stars move rapidly in many directions in order to support the galaxy against its own gravity. Moving inward, the dispersion generally becomes still higher as the potential deepens so that the innermost stars travel at hundreds of kilometers per second relative to the center of mass. The resulting two-dimensional maps show regions of enhanced dispersion near the core and more modest values farther out, with contours that roughly follow the shape of the inner isophotes. Any net rotation appears only as a gentle gradient in the mean velocity field, because the overall support of the galaxy comes from the random motions rather than from a rapidly spinning disk. In some directions, the mean velocity may change sign across the center, indicating slow rotation about a preferred axis, but this rotation contributes only a small share of the total kinetic energy of the stars. By comparing the observed pattern of velocities and dispersions with dynamical models, astronomers infer not only how fast stars move, but also how their orbits are oriented. Some stars follow more radial paths that carry them in and out from the center along elongated trajectories, while others follow more tangential paths that keep them circling around the center at nearly constant radius. The relative importance of these orbital families is described as orbital anisotropy, and it has a strong effect on how the velocity dispersion profile appears when projected along the line of sight. In many massive core galaxies, including NGC 4889, the inner regions show a bias toward tangential orbits, a pattern in which stars avoid plunging directly through the center and instead move preferentially around it. This configuration is consistent with a history in which stars that once occupied very radial orbits are removed or scattered by repeated interactions with central compact masses during mergers, leaving behind a population that is more strongly weighted toward orbits that skirt the inner core. The high central dispersion combined with this tangential bias indicates that the potential near the center is both deep and structured in such a way that stars feel a strong pull even when they do not pass very close to the exact center. To extract quantitative information from these kinematic patterns, observers and theorists construct dynamical models that treat the galaxy as a collection of many possible orbits moving in a specified gravitational potential. Using orbit superposition techniques, they populate these orbits with stars in different proportions, project the resulting motions along the line of sight, and compare the synthetic velocity fields with the observed maps until a satisfactory match is obtained. The required potential includes contributions from the luminous stellar distribution, whose mass follows the observed light, scaled by an assumed mass to light ratio from the more extended dark matter halo, and from any central compact mass that is needed to reproduce the extreme central dispersions. If the mass-to-light ratio is fixed within reasonable bounds, and the contribution from the dark halo is constrained by larger-scale data, then the remaining degree of freedom lies in the strength and compactness of the central mass concentration. In models of NGC 4889, the very high dispersions observed within the inner few hundred parsecs require a central mass that is both large and confined to a very small region compared with the overall size of the galaxy. The inner light profile alone, even with its depleted core, cannot generate such high stellar speeds unless an additional centrally peaked mass component is present. The fact that the dispersion rises toward the center and that the pattern of velocities and dispersions across the inner region fits models with a very massive compact object supports the conclusion that the gravitational field in this zone is dominated by more than just the visible stars. At the same time, the overall shape of the dispersion profile and the measured anisotropy help set limits on how this central mass is distributed and how strongly it influences stars on different orbits. The innermost measurements taken as close to the center as the resolving power of current telescopes allows are especially important because they probe the region where the gravitational pull of the central mass begins to exceed that of the surrounding stellar body. Even here the light remains dominated by stars and the core appears as a bright, smooth centre with no obvious morphological sign of the deep gravitational well beneath it. Only through the analysis of line-of-sight velocities and dispersions does the full depth of the potential become apparent, revealing an inner region where stars move rapidly under the combined influence of the galaxy and an unseen central mass concentration. In this way, the kinematics of the inner stars in NGC 489 act as a dynamical tracer of the invisible mass distribution, preparing the ground for a more focused view of the domain, where the central compact object exerts direct control over stellar motions and where its gravitational influence becomes the dominant factor shaping the inner orbits. Within the innermost region of NGC 489, the patterns of stellar motion point to a zone where the gravitational pull of the central compact mass outweighs that of the surrounding stars, a domain that astronomers describe as the sphere of influence of the supermassive black hole. This sphere is not marked by a visible edge or sharp boundary in the light distribution. Instead, it is defined in terms of gravity and dynamics. One common way to describe it is as the region inside which the mass of the black hole is comparable to or greater than the mass of stars enclosed within the same radius. Another closely related description is the radius inside which the presence of the black hole significantly raises the characteristic speeds of nearby stars above the level set by the broader stellar body alone. In practical terms, the sphere of influence is the volume of space around the black hole, where its own gravity plays the leading role in shaping stellar orbits, while farther out the combined pull of the galaxy's stars and dark matter dominates. In nearby galaxies such as the Milky Way with its central object often called Sagittarius, individual stars inside the sphere of influence can be tracked directly, as they trace out fast, tight orbits around the central mass, providing a clear dynamical map of the region. In NGC 4889, the great distance of the Coma Cluster prevents such direct tracking, so the sphere of influence must be inferred indirectly from the integrated motions of many stars blended together. Even so, the same physical idea applies. There exists a central zone where the black hole's gravity sets the scale for stellar speeds and orbital shapes, and this zone has a size that depends on both the black hole mass and the density profile of the surrounding stellar distribution. Dynamical models that match the observed velocity dispersions and the inner light profile of NGC 4C89 indicate that this sphere of influence extends over a region that in linear scale reaches across many light years, likely tens to perhaps hundreds of light years or more. While the exact radius remains uncertain because the black hole mass and the central stellar mass profile are not known with perfect precision, all reasonable models agree that the sphere is large in absolute terms compared with those in less massive galaxies, reflecting the exceptional mass of the central object and the deep potential well at the heart of NGC 489. Within this central zone, stars move in orbits that respond strongly to the point-like gravitational pull of the black hole. In a simplified description, a star on a bound orbit within the sphere of influence follows a path similar to that predicted by classical gravity, around a dominant central mass, with orbital speed increasing as distance from the centre decreases and orbital periods shrinking for closer-in trajectories. In reality, the situation is more complex because the stellar distribution and any surrounding dark matter still contributes some fraction of the gravitational field, and the orbits of individual stars are influenced by many small gravitational encounters with other stars and remnants over long timescales. Even so, the net effect is that inside the sphere of influence, the gravitational potential becomes more sharply peaked, and the average stellar speeds reach higher values than would be possible if only the smoothly distributed stellar mass were present. The transition across the sphere of influence is not abrupt. As one moves inward from larger radii, the contribution of the black hole to the total gravitational pull grows gradually. At some characteristic radius, the enclosed stellar mass falls below the black hole mass, and inside this radius, the central object contributes more than half of the total mass that governs orbital motion. Beyond this radius, stars still feel the black hole's pull, but it is only a modest correction to the smoother background potential produced by the galaxy as a whole. This gradual change in dominance is reflected in the velocity dispersion profile and in higher-order features of the line-of-sight velocity distribution. In dynamical models for NGC 4889, the inclusion of a massive black hole produces a central rise in dispersion and particular patterns in the shapes of spectral lines that match the observations much better than models without such a central mass. These signatures are most sensitive to the region inside the sphere of influence, where the gravity of the black hole is strongest. The orbital structure within this domain also bears the imprint of the black hole's presence. As mentioned earlier, the inner regions of NGC 4889 show a tendency toward tangential orbits, meaning that many stars move on paths that circle around the center rather than plunging straight through it. Such orbits are less likely to carry stars to extremely small radii, where the gravitational field is strongest, and their predominance suggests that stars on more radial paths have been scattered or depleted over time. This orbital anisotropy is thought to arise in part from the past action of a central black hole or black hole pair during merger events, which efficiently eject stars that approach too closely on radial orbits, leaving behind a population bias toward paths that skirt the center. Within the sphere of influence, therefore, not only the speeds but also the directions of stellar motions reflect the strong gravitational effects of the central mass. Stars that still occupy more radial trajectories can experience close passages near the black hole where tidal forces become very strong. If a star ventures too near, the difference in gravitational pull between its near and far sides can exceed the star's own self-gravity, tearing it apart in an event known as tidal disruption. In most of NGC 4889's history, such events are likely rare compared with the total number of stars in the galaxy, but they form an important aspect of the physical environment within the sphere of influence, because they mark the ultimate fate of a small subset of orbits that cross very close to the center. Even when stars are not disrupted, repeated close passages can gradually alter their orbital energy and angular momentum through weak encounters with the black hole, and with one another slowly reshaping the distribution of paths that fill the central volume. The timescales associated with orbital motion inside the sphere of influence are shorter than those at larger radii. A star on a tightly bound orbit near the center can complete many revolutions around the black hole in a time that is short compared with the age of the galaxy, while stars farther out near the edge of the sphere take much longer to complete a single orbit. This stratification of orbital periods means that the inner region reacts more quickly to changes in the central potential, while the outer galaxy responds more slowly. However, because the current state of NGC 4889 appears dynamically relaxed, and there is no evidence for recent major disturbances in the central structure, the orbits within the sphere of influence are expected to have settled into a relatively stable configuration, with the overall distribution changing only very slowly over cosmological times. From an observational standpoint, the sphere of influence sets an important scale for the design and interpretation of kinematic measurements. To detect the dynamical signature of the black hole in NGC 4889 telescopes must achieve an angular resolution that is fine enough to isolate the region where its gravity dominates. if the resolving power is coarse compared with the apparent size of this sphere, the central rise in dispersion and the subtle changes in line profiles will be diluted by light from stars outside the sphere, making it harder to distinguish models with and without a black hole. In the case of NGC 4889, the combination of its distance and the finite resolution of current instruments makes this task challenging, but not impossible, and careful modelling of the available data has been used to estimate the radius of influence and the associated black hole mass. The resulting sphere of influence is large enough in physical size that it would comfortably encompass the entire planetary region of the solar system if it were placed at the centre, but it still occupies only a tiny fraction of the total volume of the galaxy. Beyond this inner domain, the motions of stars remain shaped mainly by the extended stellar body, and the dark matter halo and the presence of the black hole becomes just one part of the overall gravitational landscape. Within the sphere of influence, by contrast, this central supermassive black hole is the dominant source of gravity, and the orbits of stars, the frequency of close encounters, and the timescales on which dynamical processes unfold, all bear the mark of this compact massive object hidden at the heart of NGC 4889. In the central regions of NGC 4889, the presence of a very massive compact object implies a long history of gas inflow and energy release, even though the galaxy today appears quiet and lacks the brilliant point-like beacon of an actively accreting nucleus. The basic physics of accretion onto a supermassive black hole is well understood in broad outline. When gas with some angular momentum falls toward the deep gravitational potential at the centre, it cannot plunge straight in, but instead settles into a rotating structure known as an accretion disk. In this disk, matter spirals inward as friction. Like processes and magnetic stresses redistribute angular momentum, allowing gas to move to smaller orbits while some of the energy liberated by this inward motion is carried outward. As gas falls deeper into the potential, gravitational energy is converted into heat, raising the temperature of the disk to the point where it shines strongly across a wide range of wavelengths. In the most luminous phases, when the accretion rate reaches a significant fraction of the maximum steady rate allowed by radiation pressure, the central region can outshine the entire host galaxy, producing what is observed as a quasar or luminous active galactic nucleus. Around such an engine, high-energy radiation winds and sometimes narrow collimated jets carry energy and momentum back into the surrounding gas, a process often referred to as feedback. Over time, this feedback can heat, expel, or redistribute gas on scales ranging from the inner parsecs to the larger galactic and even cluster environment, playing an important role in regulating both black hole growth and star formation. In NGC 4889, there is no bright quasar today. The nucleus does not dominate the galaxy's light, and observations do not reveal the intense blue continuum broad emission lines or powerful jets that characterize the most active galactic nuclei. Instead, the central regions show the smooth red light of old stars and only relatively modest signatures of nuclear activity consistent with a black hole that is presently accreting at a very low rate compared with the levels reached in a classical quasar phase. Yet the very large mass inferred for the central object implies that, integrated over cosmic time, substantial amounts of gas must have been accreted. For a black hole to grow from a seed of perhaps a few tens, hundreds, or thousands of solar masses in the early universe to a mass of many billions of solar masses by the present day, long periods of efficient accretion are required, especially when the universe is younger and gas supplies are more abundant. Although the exact pathway for NGC 4889 cannot be reconstructed in detail, the combination of its massive black hole, its central position in a rich cluster, and its status as a giant elliptical with an old stellar population is consistent with a history in which the nucleus experiences one or more luminous active phases in the past. During those phases, gas driven inward by galaxy mergers, tidal interactions, or cooling flows from the surrounding hot atmosphere would have fed the accretion disk, allowing the black hole to gain mass while releasing large amounts of radiation. Numerical models and observations of other clusters show that such active episodes can create cavities, and bubbles in the hot intracluster gas inflate radio lobes filled with relativistic particles and drive shocks that heat the surrounding medium. In the Coma Cluster, the present distribution of hot gas and the relative calm of the central region suggest that any major outbursts associated with NGC or C889 took place long ago, giving the intracluster medium time to relax toward a smoother state. But the general expectation remains that some share of the energy that helps to keep the central gas hot and dilute in earlier times likely comes from activity in the nuclei of central galaxies, including NGC 489. Within the galaxy itself, past active phases would have affected the interstellar medium by ionizing gas driving outflows and possibly sweeping some material out of the central regions. Over multiple cycles of activity and quiescence, this energy input could help explain why NGC 489 now contains relatively little cold gas and shows only low levels of ongoing star formation, even though it resides in a region where gas stars and dark matter are all abundant on larger scales. The details of this regulation remain an area of active research, and for any individual galaxy including NGC 4889, the precise sequence of events is uncertain. Current evidence indicates that the nucleus is in a low state of activity today, while the mass of the central black hole and the broader context of galaxy and cluster evolution point strongly to a past in which accretion onto this object proceeds at much higher rates. In that earlier era, when the universe is younger and gas infall more vigorous, NGC 4889 may have appeared to distant observers as a bright quasar at the core of a growing cluster, its central engine illuminating the surrounding space with radiation produced as matter spirals inward through a hot luminous accretion disk. As accretion fuel dwindles, or is stabilized against further collapse, the active phase subsides, leaving behind a massive, slowly growing black hole embedded in a galaxy whose visible light once again comes primarily from stars. The inner regions that now appear calm in images therefore preserve evidence of earlier periods of stronger activity, encoded in the mass of the central object, the structure of the depleted core, and the state of the surrounding gas, all of which together indicate the importance of past accretion and feedback in shaping both the black hole and its host galaxy. Determining the mass of the central black hole in NGC 4889 relies on the same stellar motions that reveal the existence of its sphere of influence. But now the aim is to translate those motions into a quantitative measure of how much unseen mass resides at the center. The basic idea is simple in concept. Stars move under gravity, and the faster they move near a given radius, the more mass must be enclosed within that radius to keep them bound. In practice, the situation is complex because the gravity comes from several components at once: the stars themselves, the dark matter halo, and the compact central object, all distributed in 3 dimensions. To disentangle these contributions, astronomers build dynamical models that incorporate the observed light distribution of NGC 4889, the measured kinematic maps of mean velocities and velocity dispersions, and an assumed form for the dark matter halo, and then ask what combination of stellar mass to light ratio and central compact mass can reproduce the data. The observed surface brightness profile extending from the bright central regions through the shallow core and out into the outer body provides the two-dimensional projection of the stellar luminosity. By deprojecting this profile under plausible assumptions about symmetry, a three-dimensional stellar density distribution is obtained, and from this the stellar contribution to the gravitational potential is computed once a mass-to-light ratio is adopted. The dark matter halo is often represented by a smoothly varying density profile that grows in importance at larger radii, constrained by the need to match galaxy velocities farther from the center and by independent evidence from the cluster environment. The central black hole is then added as a point-like mass at the very center. Within this composite potential, a large library of stellar orbits is calculated covering a wide range of shapes and energies, from nearly circular, tangentially biased paths to highly elongated radial trajectories that pass close to the center. In orbit superposition modeling, each of these orbits is assigned a weight that represents how many stars populate it, and the superposition of all weighted orbits is chosen to reproduce the observed surface, brightness, and the full set of kinematic measurements, including not only the mean velocities and dispersions, but also the detailed shapes of spectral lines that carry information about the distribution of stellar speeds. For a given assumed black hole mass, there is usually some combination of orbital weights and stellar mass-to-light ratio that can match the data reasonably well, but when the black hole mass is changed, the predicted central dispersions and line profile shapes shift in systematic ways. If the assumed black hole mass is too small, the models cannot produce the high stellar speeds observed near the center without invoking unphysical orbital configurations or mass-to-light ratios that conflict with stellar population constraints. If the central mass is set too large, the predicted dispersions become higher than observed, and the line profiles develop wings that are not present in the data. By exploring a grid of models with different black hole masses and comparing their predictions to the measurements, astronomers identify the range of masses that provide an acceptable fit with a preferred value where the agreement is best. In NGC 489, this exercise indicates a central mass in the regime of several tens of billions of times the mass of the Sun, placing the black hole among the most massive known in the nearby universe. Estimates from different modeling approaches and datasets do not agree on a single precise number, and the uncertainties are significant, reflecting limitations in spatial resolution, in the exact shape of the stellar density profile at the smallest radii, and in assumptions about the orbital anisotropy and the dark matter halo. Even so, the consistent result is that the central object is far more massive than the black hole in the Milky Way, and rivals or exceeds the black holes inferred in other giant elliptical galaxies at the centers of rich clusters. This conclusion is supported by the size of the depleted core, which requires a substantial central mass to remove enough stars through dynamical interactions, and by the very high central velocity dispersions that cannot be explained by the stellar body alone. The inferred mass also places NGC 489 at the extreme upper end of empirical relationships that link black hole mass to properties of the host galaxy, such as the stellar velocity dispersion measured on larger scales or the total bulge mass. These relationships, built from samples of galaxies with reliably measured black holes, show that more massive galaxies with higher dispersions tend to host more massive black holes, though with some scatter. NGC 4889 sits beyond the range populated by typical galaxies, both in terms of its global properties and in terms of its central mass, so it serves as a test of how these scaling relations behave at the highest masses. In some analyses, the black hole in NGC 48 and 89 appears somewhat more massive than a simple extrapolation of the average relation would suggest, while in others it lies closer to the high mass tail of the distribution, a difference that depends on exactly how the galaxy properties are measured and how the relations are defined. Regardless of these subtleties, the key point is that the dynamical data demand a central mass that is not just large but extreme, in keeping with NGC 4889's role as a brightest cluster galaxy in a very rich environment. At the same time, the uncertainties remind observers that weighing such a distant and massive black hole is inherently challenging. The sphere of influence, although large in physical units, subtends only a small angle on the sky, at the distance of the Coma Cluster, so even the largest optical and near-infrared telescopes can probe only the outer parts of this region with full clarity. Small differences in how the light profile is measured, in how seeing and instrumental effects are corrected, or in how the contribution of the surrounding cluster light is subtracted, can shift the inferred central density and thus alter the derived black hole mass. Assumptions about the dark matter halo and about how the mass-to-light ratio may change with radius or between different stellar populations add further degrees of freedom. To address these issues, observers compare results from independent datasets and modeling codes, perform tests with mock galaxies to evaluate systematic errors, and explore how robust the mass estimates are to changes in model ingredients. For NGC 4889, these efforts do not eliminate all uncertainty, but they converge on the conclusion that the black hole mass is of order many tens of billions of solar masses rather than merely a few billions, even if the exact figure remains a subject of ongoing refinement. This large mass sets the scale for all subsequent considerations of the central object, from the size of its event horizon to its past accretion history and its ongoing influence on the surrounding stars and gas. It also reinforces the idea that the growth of supermassive black holes and the assembly of the most massive galaxies and cluster cores are closely intertwined processes, both fed by the same long history of mergers, gas flows and dynamical evolution in dense environments. In NGC 4889, the central black hole's mass stands as a cumulative record of that history, measured through the motions of stars that now orbit in the deep potential well carved out at the heart of the galaxy. Given a mass estimate for the central black hole in NGC 4889, the next natural step is to translate that mass into a physical scale for the region from which light cannot escape the event horizon. In general terms, a supermassive black hole is a compact concentration of mass so dense that within a certain radius the escape speed equals the speed of light. The boundary at which this condition is reached is called the event horizon. It is not a solid surface but a one-way boundary in space-time. Anything that crosses inward, including light, cannot return, while outside this radius matter and radiation can still move on orbits and in principle escape if they have enough energy. For a non-rotating so-called Schwarzschild black hole, the radius of the event horizon increases in direct proportion to the mass. If the mass doubles, the event horizon radius doubles. In simple terms, each solar mass added to a black hole increases its characteristic radius by a fixed amount of a few kilometers. For stellar mass black holes, this radius is only a handful of kilometers, but for supermassive black holes in galaxy centers, the same proportionality means that the event horizon can grow to sizes measured in millions or billions of kilometers. For NGC 4889, dynamical models indicate that the central black hole has a mass in the regime of many billions to several tens of billions of times the mass of the Sun. There is genuine uncertainty in the precise value, because different analyses and modeling assumptions yield results that differ by roughly a factor of a few, but they consistently place the mass at the very high end of the known distribution. Even taking the lower end of this range, the corresponding event horizon radius is already measured in billions of kilometers. At the higher end, where the mass reaches several tens of billions of solar masses, the event horizon radius becomes larger, still extending to scales that are naturally compared to the size of the planetary region of the solar system. To make this comparison concrete, it is helpful to recall that the characteristic distance between Earth and the Sun, often used as a standard yardstick in astronomy, is about 150 million kilometers. Jupiter orbits farther out at several times this distance, and Neptune orbits at a distance of roughly 30 times the Earth-Sun separation. Beyond Neptune lies a more diffuse region that includes many icy bodies on orbits that can reach several tens of Earth-Sun distances and beyond. In this context, a black hole of about 1 billion solar masses would have an event horizon radius of order a few billion kilometers, comparable to several tens of Earth-Sun distances already reaching beyond the orbit of Neptune if placed at the center of the solar system. A black hole of 10 billion solar masses would have an event horizon radius about 10 times larger, corresponding to hundreds of Earth-Sun distances, and one of several tens of billions of solar masses would have an event horizon that in radius comfortably spans a region larger than the zone occupied by the major planets and much of the inner part of the distant icy population. For NGC 489, where the black hole mass is inferred to lie in this many billions to several tens of billions, solar mass range, the implied event horizon size therefore naturally falls in the category of solar system scale and beyond, because all of these estimates depend on the exact mass, and because that mass remains uncertain, it is more accurate to say that the event horizon radius is comparable to, and very likely larger than the distance scale defined by the orbits of the outer giant planets, rather than to quote a single fixed value. If the true mass lies toward the lower end of the allowed range, the event horizon radius would be of the same order as the orbital radius of Neptune or somewhat larger. If the mass lies toward the upper end, the radius would extend to several times that distance, reaching into the region that in the solar system would include much of the distant cometary reservoir. In either case, the fundamental point remains that the event horizon of the NGC 489 black hole is not a small star-sized object, but an extended region on the scale of many Earth-Sun distances, with a diameter that light would need many hours to cross. Although the event horizon has this enormous linear size, it is still tiny compared with the broader structures in which it sits. The sphere of influence of the black hole in NGC 489, defined by the region where its mass dominates over the stellar mass, extends over distances measured in many light-years vastly larger than the event horizon radius. Beyond that, the galaxy itself spans tens of thousands of light-years, and the Coma Cluster stretches across millions of light-years. In this nested hierarchy of scales, the event horizon occupies only a minuscule fraction of the volume of the sphere of influence, which in turn fills only a small fraction of the central region of the galaxy. From the perspective of the galaxy's light distribution, the event horizon is effectively point-like invisible against the background of countless stars. There is no abrupt change in brightness at the event horizon radius, no visible ring or edge, because the starlight that observers see comes from much larger radii, and the gas density near the horizon is very low in the present quiescent state. The event horizon plays its central role in the dynamics and physics of matter immediately around the black hole, but those processes unfold on size scales much smaller than those directly resolved in current observations of NGC 4889. The concept of an event horizon also depends somewhat on the spin of the black hole. If the black hole rotates, the geometry of space-time near it changes, and the event horizon radius for a given mass can differ from the simple Schwarzschild case by a factor of order unity. A maximally rotating black hole has an event horizon radius that is smaller than that of a non-rotating black hole with the same mass, while the region outside the horizon where space is dragged around by the rotation becomes more extended. For NGC 4889, the spin of the black hole is not directly measured, so models usually adopt the non-rotating case as a useful reference. Even if the black hole spins rapidly, the change in event horizon radius would not alter the conclusion that the horizon scale lies in the solar system regime because the mass scale is so large. Thus, while the exact radius and shape of the horizon depend on parameters that are still uncertain, the order of magnitude comparison to the planetary region remains robust. The event horizon then provides a bridge between the abstract quantity of mass measured in many billions of solar masses and a more intuitive length scale that can be compared with the structure of the solar system. For the black hole in NGC 4889, that bridge leads to the picture of a central object whose boundary of no return would, if placed in the Sun's position, encompass or exceed the zone occupied by the major planets. This solar system scale event horizon sits buried deep within the core of the galaxy, far smaller than the stellar structures that have been examined so far, yet it defines the innermost region of the gravitational well in which stars and gas move, and it sets the ultimate limit beyond which the central mass exerts absolute control over the fate of any matter that ventures too close. At the very centre of NGC 4889, the supermassive black hole that has been inferred from dynamical measurements now resides in a state of very low activity, a dormant phase in which matter still drifts inward under gravity, but only a tiny fraction reaches the event horizon at any given time. The central mass dominates the gravitational field within its sphere of influence, so stars and remnants continue to move on orbits shaped mainly by its presence. Yet the amount of gas available to feed it is limited by the broader conditions in the galaxy and in the Coma Cluster core. Most of the cold gas that would once have been the raw material for rapid accretion is gone removed or heated during earlier stages of galaxy and cluster evolution, and what remains in the central regions is a combination of hot, low-density plasma and the diffuse mass loss from aging stars. As these stars shed material in slow winds, some fraction of that gas can lose angular momentum and drift inward, eventually encountering the deep potential well of the black hole. However, the surrounding hot atmosphere and the energy input from past feedback episodes maintain conditions in which the infalling gas is quickly heated and becomes part of a tenuous high-temperature flow, rather than condensing into a dense cool disk. In such an environment, the accretion rate onto the black hole is thought to be far below the level that would produce a luminous quasar. Instead, any ongoing inflow proceeds in a radiatively inefficient mode in which much of the energy released as gas falls inward is carried outward by the flow itself or by weak outflows rather than being converted into bright radiation. Observations of NGC 4889's nucleus at different wavelengths show no overpowering central source that would outshine the host galaxy, and X-ray and radio measurements place limits on any compact emission that might arise close to the event horizon. Within those limits, it remains possible that a faint compact core is present, powered by the low-level accretion of hot gas and stellar debris, but its luminosity is modest compared with the total light of the galaxy and the intra-cluster medium. The gravitational potential of the black hole, by contrast, remains enormous, and it continues to govern the orbits of stars and remnants on very small scales, even when little radiation is produced. Stars that venture deep into the sphere of influence feel the strong tidal field, and on rare occasions a star on a highly eccentric orbit may pass close enough to be torn apart by tidal forces, its material then forming a transient accretion flow that briefly increases the radiative output of the nucleus before fading again. The predicted rate of such tidal disruption events in a massive core galaxy like NGC 4889 is low when averaged over the whole galaxy. because many stars have been scattered onto more tangential orbits that avoid the very center, but over very long timescales such episodes still occur and contribute to the slow, intermittent growth of the black hole. Even between these rare events, the black hole continues to gain mass gradually from the steady trickle of hot gas that it captures from its surroundings. The characteristic timescale on which its mass would double at present accretion rates, however, is thought to be much longer than the current age of the universe, so its present growth is effectively stalled, and its mass today is very close to the value fixed by earlier, more efficient accretion phases. In this dormant state, the direct radiative influence of the black hole on the surrounding galaxy is limited. There is no intense central radiation field to ionize large volumes of gas, or to drive powerful wide-angle winds. Instead, any feedback that occurs is more subtle, transmitted through gentle heating of the surrounding hot atmosphere by weak outflows or by the dissipation of energy in the innermost accretion flow. On scales of tens to hundreds of light years, this feedback may help maintain the temperature and structure of the central gas, slightly reducing the tendency of the hot plasma to cool and condense. On somewhat larger scales, any small cavities or ripples that might be produced in the intra-cluster medium by low-level nuclear activity would be minor compared with the large bubbles and shocks associated with the most powerful cluster central outbursts seen in other systems. The dominant role of the black hole at these radii is gravitational rather than radiative. It sets the depth of the potential well at the center of NGC 4889, anchors the depleted stellar core that extends over thousands of light years, and defines the region around which the innermost stellar orbits are arranged. The presence of such a massive object also influences how the galaxy responds to any future infall of gas-rich satellites or to fluctuations in the supply of hot gas from the intra-cluster medium. If a fresh reservoir of cold gas were somehow delivered to the nucleus, the black hole could in principle re-enter a more active phase, but in the present epoch, the observed lack of such fuel and the stability of the hot atmosphere argue for continued quiescence. The gravitational potential itself, by contrast, changes only very slowly as the black hole mass grows, so the orbits of stars and remnants in the central regions remain essentially fixed on human and even on galactic timescales. From the perspective of the galaxy as a whole, the black hole now functions as a massive compact anchor at the center of the stellar and dark matter distribution, a relic of earlier growth whose current accretion rate is low, but whose influence on the dynamics of the inner regions is permanent. Close to the event horizon, where gravity is strongest, the structure of space-time differs markedly from that in the outer galaxy. Yet this extreme regime occupies only a tiny volume compared with the vast extent of NGC 4889 and the Coma Cluster. The hot gas that approaches within a few tens or hundreds of event horizon radii experiences strong gravitational redshift and intense tidal forces before either crossing the horizon or being deflected outward. But the amount of such gas is small in the current low accretion state, so the associated high-energy emission remains faint. At larger radii, where stars and gas follow more gently curved paths, the presence of the black hole is felt mainly through the high velocities required to remain in orbit and through the way in which orbital families are arranged to avoid the very center. In this way, the central black hole in NGC 4889 stands as a nearly silent component of the galaxy, dynamically essential in the inner regions required to explain the observed stellar kinematics and core structure, but radiatively quiet at present, with only a gentle ongoing influence on the hot gas and stars that inhabit its immediate neighborhood. Its event horizon on the scale of a planetary system sits deep within the luminous core of the galaxy, marking the innermost limit of the gravitational well that has been assembled over billions of years of galaxy and cluster evolution, and now persists in a long-lasting state of near dormancy at the heart of NGC 289